Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our Lecture 3, Parallelization Fundamentals. And as I said earlier, this would be much more a natural lecture to begin with after the introduction of the course, but because of the assignments and the feedback from students that we got, we include the MPI a little bit before to already start with some practical lectures on MPI to understand parallelization already bottom up, so to speak, while this lecture will be much more conceptual and top down. So really making you able to understand why we want to parallelize. What are the benefits of parallelization and what is domain decomposition? And many of the terms that really are key to high performance computing. But before we go there, let us just review lecture 2.1 that we had the last time. We actually were diving into MPI much more. We basically had a very practical lecture of understanding MPI based on the conceptual aspects we had in the lecture 2. And we started a little bit with point-to-point communication, where we always said that there is a need for a matching send and receive, right? When one MPI process is starting an MPI send, then you need to have a matching MPI receive. And the way how that works is a little bit looked and described here in this element of the slides, where you also have to, of course, think about that you transmit really data in the send and receive. And with this also have to prepare a little bit of buffer for getting this incoming data when you basically are at the other process. In other words, you have to have space for that, where the data should be written in when it comes over the network and will be written within your memory. Because if you remember, the idea was that you have distributed memory, so you essentially cannot directly access as a process or as a processor here, more notably, the memory of the other one. So you always have to do send and receive and message exchanges in order to access this memory, either let it be for reading or for writing data. So this is a specific concept, which is, let's say, a little bit elaborate, because we always have to have the source and the destination. You remember a little bit from our practical examples, a ping pong, I hope, where we started from the source to the sink and we had a ping. And then, of course, then we want to have the pong. That means from the original basically destination, we move towards something which is now the source, and the sink is the original sender. And this has to be programmed explicitly. And we basically learned that by doing so, the important part of it is really the rank information, which we get through this MPI environment that we initialize and then also at some point in time finalize. But this is really key to create this environment. And the beauty is we not only know how many processors, or more notably processes, are actually inside such a communicator, we also know the unique identity of each one of those, which you see a little bit in this graphic here. MPI world is the one of all, is really the world of all processes, right? And they all have their unique rank. As we discussed earlier in previous lectures, you are able to create your own groups of it. You can basically have different communicators created, and we will do so in subsequent lectures. But today it's important to realize that the rank information is key to also influence the application logic of your application. If you remember, we have this SPMD setup, same program, multiple data. So in some way, you also want not to execute always the same, but of course, to influence that the same program will go in different application logic parts within your program. This is something where the rank comes in. And here you see basically to identify the actor that is playing the ping, we have rank 0. And then we have the actor, so to speak, that plays a pong. We have rank 1. And with this, we are able to code the MPI send with a matching receive, which is a ping. And then, of course, for the pong, we move directly in the send and then come back to the receive in the original sender to actually receive the pong. And with this, we have a ping pong scenario with two processes and a very simple message exchange, which is perhaps one of the hearts of MPIs. But we also learned that this has, of course, obviously limits. So we know that new cutting edge applications have thousands of processes, if not 10,000 or 100,000 of processes in the large scalability applications that we see basically day to day in HPC centers. So what can be the solution to not explicitly program always a source and destination, to think large scale, think big. Big means high performance computing. If it's just a couple of cores, maybe shared memory is better. Maybe you don't need even HPC, you can still use your laptop. But if you think big in terms of high performance computing, if you want to use those clusters efficiently, we have to think big. And in order to do this communication in this style, it's very important to understand that there are collective communication operations which directly act on each of the players within a specific communicator. So I don't have to explicitly say my message from here goes to 5, then it goes to 8, then it goes to 3, then it goes to etc. You know my message. I think the interesting thing of collective operations are really two things. Firstly, it enables us to scale significantly among many processes. And secondly, they're very nicely performance-wise implemented. So they follow more a tree kind of structure if you look into the implementation, making it really efficient to talk to all these communicators, to all the process inside the communicator, instead of doing, for instance, a for loop and do a send and receive with here all the 9 or basically essentially 10 processes from 0 to 9. And we will actually talk about this with the difference with this for loops and with the collectives in later lectures. But I think these are really the groundbreaking simple processes that you need to know for MPI. And then we also discuss it in the light of the, of course, key principles of high performance computing, which are schedulers. So in order to use a scheduler, you would use your Hello C program. You have a C compiler being MPI enabled then at some point in time to understand, of course, to include not only the MPI header here, but also to understand to create this MPI environment. And you give it to the scheduler, you will schedule this MPI job as part of this HPC machine. And by doing so, we also learned last time in the practical lecture a little bit about the sensitivity of the runtime. When you're doing this, of course, you share your application with many other users on these machines. And of course, there you can imagine if you have a, let's say, proper simulation here of a lighthouse and some ocean waves and a boat floating on these ocean waves in some point in time, and you have all the physics rightly implemented, you basically have some point in time where you have to specify how long your application really should run and basically be simulating this. And you have learned this, that this is something we put in the so-called job scripts and specify the time it should run. And whenever this time is over, basically that you specified, the scheduler will have no harm to just cancel your job. And this is something what you learned last time, hopefully, we're running against the wall with this specific job, and there's nothing we can do. And we specified it, of course, ourselves. So in the next execution, we can maybe increase the time if it is allowed. And on the other hand, if you basically, have a time that you specify that is by far too much, then it's also not good, because your job will maybe easier finish, but you really have a problem in the scheduling that many others are blocked from being scheduled very early on. So here's, of course, the idea of over time, develop a little bit the sensitivity for how long your job is actually running. Can you sneak in with backfilling to some scheduling strategies to be earlier scheduled? Maybe you have a paper to write, you want to be early scheduled. Maybe it's good to then have a smaller runtime that actually fits in one of these scheduling holes that we discussed. And this was really practical understanding. And I think important is, and this is really a key importance of this course, to understand and get hands-on the MPI in your assignments, which make really you much more feeling what I mean by these conceptual slides. Also the idea of submitting again to a scheduler and submitting again, see the job status, the job outcome, submitting again. All this workflow is what HPC experts do every day. They use a scheduler significantly. They have changes to their program, compiling again, and then using the scheduler again. So And this is something where basically we had a very practical lecture early on to get you right on track for the assignments. But now let's reflect a little bit also on why we should do this and what are the concepts of actually doing this, because why we just send around messages and why is it so important? So hence it takes us to the so-called Parallelization Fundamentals, where we will have some very simple parallel computing examples just to understand the idea of multi-cores and many cores perhaps. And then also this important term called domain decomposition. Wherever you go, physics, chemistry, and basically earth sciences, with climate simulations maybe, domain decomposition plays a good role. And with this goes the parallelization methods you can apply. Then we have this interesting phenomena of saying, at some point in time, we reach the end of the core space or the memory space. So we have to have something we call the halo and ghost layer that makes us able to store some variables that we want to communicate maybe in the next time period to the next processes next door. And we will talk about this in this course specifically today, in basically this lecture, where we also differentiate between many different domain decompositions. We will reflect on the term that I introduced the last time with a single program, multiple data, and then look what could be differences to maybe MPMD, multiple program, multiple data, and other data parallelism strategies. With this, we also will enter the world in part 2 today into the ideas of more, let's say, established terms and theory aspects of parallel computing. We keep the theory here as a 6th credit course, more or less to a moderate degree, so it will be not so elaborate, but still we have elements like Moore's law, like Amdahl's law, or Gustafson's law, where we will look a little bit about the theoretical conceptual ideas of doing HPC, which has lots of interesting understanding of why you want to use HPC in the first place, why we are all interested in the speed up. And everybody is, even those that don't admit it, they would be probably in denial. You always want to speed up your applications, or basically when we come to strong scaling and weak scaling, with weak scaling, you maybe also think about what else we could do, more particles, more details, more simulation space. So in the end, you always come to simulations which are getting more and more realistic. And with this, of course, being much more to real world scenarios and helping society or really the problems that we're going to simulate with HPC. We will learn about some limits with Amdahl's law and why basically serial limits are always a big problem in our case. And then really will motivate a little bit the idea of performance analysis, although performance analysis will be a specific part of the lecture much more down the road when you have, let's say, established the basics of the course. So a very interesting lecture. It's a bit conceptual and I would say also here and there theoretical, but it really captures the essence of a very practical concern, although being a conceptual lecture, and this is a domain decomposition, and we will make the case of it. And with this, you already understand the complex aspects of parallel programming, why we cut basically our domain we want to simulate into different pieces, how we do it, what options there are to do this, what impacts I have by steering this. And it's really a sort of abstraction from this. And it's important to know that to use it in your HPC programming skills. So when we come to the first part of this, we would think about common strategies for parallelization. And basically, I reflect a bit on lecture 1, where we said, actually, parallel computing is not really parallel if you don't think about of it as basically doing a problem solving in a cooperative way. So the idea is, of course, not that you see here that the processors just run on their own, don't do interaction, don't do anything. Basically, we want to do this message exchanges we had last time to solve a problem in the, kind of cooperative way, all on one problem, to use more processors, to use more power with the best performance possible. And the measure of speed is something which we there think is, of course, related to this top 500, to the benchmarks, as we said with Lindbeck and so on in earlier lectures. But that's where the term high performance really comes from. But still, the idea, the essence why we as application scientists maybe want to use HPC is really in the idea of solve a problem in the cooperative way, by using as much as I can compute elements and cores in parallel computing. So this automatically brings us to the ingredients of such a machine, which we learned is a multi-core CPU, for instance, which basically has high single thread performance in all of these different cores. So they're very, let's say, very powerful cores, and hence there could be not many of them because they will basically overheat the chip these days. Hence, people have already going to this many core business as well, where basically we have these accelerators with more moderate performance levels. But it doesn't matter really for understanding the first problem. If you want to see, for instance, here, you want to have the maximum of a certain array, right? And this is a very simple example of parallel computing, why we would do this in a very, let's say, small example to show you. So here we have essentially the global maximum should be something we would say, if we cut down the domain, which is this whole array, to different cores, and that would be a first example of a domain decomposition, very trivial, just one array. But here we cut the domain in different pieces, it decomposes of this domain into different cores, or CPUs basically. And then we want to use basically for all of those, the problem, we solve the problem locally, which is here, of course, the maximum of this local array, and the same here, and the same here, and the same here. And then basically in the end, we just report the global from all of these four. So this seems kind of obvious if you basically think about a pizza problem where basically all of your people in the room have, let's say, a quarter of the pizza, and then you challenge the question, is this a good actually pizza parlor? Is this a good pizza guy that makes us a pizza? You would ask how many salami pieces are on your pizza. And you would go out and ask each one of those, and then you would combine this and say, hey, this pizza had so many salami on it. So it is very obvious that basically if you face a big problem, and here we are in divide and conquer again, that we had in the initial slide sets from this course, where of course you would break a big problem into smaller pieces. And that's what's done here today, and what essentially is the key idea of doing parallel computing, by using, of course, for each different ideas of computing. Also here we have seen then, because of high single thread performance and increasing the clock speed of every little core is not really an option anymore, because the chips will simply overheat and will be not working. Ideas have been coming up to do, let's say, moderate CPU clock speeds or cores clock speeds in the end, to have many, many hundreds of those on a chip. And with this basically being more or less an accelerator for certain problems. And they handle data parallelism and task parallelism really well. It's called the GPU, and many of you know there's already. One example is here the Volta GPU architecture. And I also want to share with you one specific GPU here of choice, which is actually very key for deep learning. The world moved ahead also, and we have already A100 instead of Volta 100 cards. But still the key essence with the idea of having very specific tensor cores remain. And I think this short illustration or animation really helps you to understand this significantly more. Obviously, we talk in lecture 9 much more about this, about GPUs, what is the difference, why it's so beneficial for deep learning. But it gives you an initial idea why parallelization fundamentals have a huge impact in GPUs.
Predicting the Earth's most severe weather. Finally finding a cure for cancer. And developing more meaningful interactions with technology. These are some of the world's next great challenges, and solving them will require exponential growth in computing power. But the gap between CPU performance and the performance that Moore's law promises continues to widen. There was a need for a new, more powerful approach: GPU-accelerated computing. The NVIDIA Volta GPU architecture is the next giant leap forward in computing performance. It employs over 21 billion transistors paired with second-generation high-bandwidth memory. Volta introduces new tensor cores designed to dramatically accelerate deep learning, delivering 125 teraflops of performance in a single GPU. With next-generation NVIDIA NVLink for direct communication between GPUs, Volta is designed for strong scaling to achieve the highest application performance and ultimately save you money. It delivers breakthrough acceleration in over 500 HPC applications and all deep learning frameworks for both training and inference with TensorRT programmable inference acceleration. Volta powers the world's largest supercomputers. It is also being adopted by all leading cloud service providers and every major data center system manufacturer. This is the one unified computing architecture for HPC and AI, bringing solutions to the world's greatest challenges within reach. Learn more at nvidia.com/Volta.
Yeah, just a short remark that I'm, of course, not really paid by NVIDIA, but it's, I think, needless to say that they are dominating the market. They have good, marketing material that you see here that we leverage as university professors. And we just have to acknowledge that NVIDIA really dominates the market right now. But it's also said, basically, for the future, that might be not the case. So there are more and more vendors going to the accelerator business. AMD, for instance, which I will also introduce probably next year or the year after next. We will get our first hands-on experience in the LUMI supercomputer in Iceland, which is basically a joint adventure with Finland and many other countries, basically 10 of them, that create the LUMI supercomputer in Finland, and Iceland is part of it. And they employ basically not any more GPUs from NVIDIA, but also from a different vendor. But it's a little bit earlier to put this in university lectures, because essentially here we teach something which you also maybe face when you go basically into the real job market. And that's why NVIDIA is still, I guess, very much distributed. And the way how you program it with CUDA and so on will be more substantive of lecture 9. So here I will continue a little bit saying just that, of course, parallelization and the real benefits, if you move into the GPU and look inside the hearts, as we have seen in the video, that shows you of having just a lot of cores available to solve simple problems is much more better than having just a couple of very high thread processing cores, maybe for certain problems. There's still some problems that actually benefit from a high single thread performance CPU. And we will do this also when we look basically in the second part of this course in the applications. Basically, when you now think about how a GPU would tackle a problem, you would have simple instructions. You can imagine basically this, you have this kind of matrix here, and you want to multiply it possibly with this kind of vector here. You have this color encoding, and this color encoding has a very certain name. It's called nicely parallel. So it's not depending on the other matrix parts, nor on the other vector parts. Only the colors that are in the same color are needed to fill really the result. And this is something which many problems basically have in many scientific and engineering scenarios. And with this matrix vector multiplication being very simple, is just perfect for a GPU. You have this independent computing, as we also sometimes call it, nicely parallel, independent parallel, of saying that I'm not depending on anyone else. So I can actually put this on different processors, and actually compute this in parallel very quickly in order to get the global solution, or basically the idea of the overall array. But essentially putting these color codings on one GPU part will enable us to really speed up the process and doing it in parallel, and then you just have the result basically together. You could call that B part and C part and so on. And essentially, that's still okay to have it with moderate performance, because the instructions that you see here with multiplication and so on, and then the global plus and stuff, is not really computation intensive. The key point is it might be really many values, big matrices, big vectors that you compute here. So basically, you're more interested in the throughput. Then another example, of course, to go a bit more into complexity, would be more climate and weather prediction. We call that the NWP, the numerical weather prediction. When you want to do something what weather.is is showing, then basically we have there a lot of lecture parts in lecture 15 devoted to this. But also here you understand a little bit more that, of course, domain decomposition is depending on the application domain. Here we have different ones, short-term weather forecast or long-term climate, but the key essence is really what you see a little bit here. So you have a horizontal grid, a vertical grid, and then within this, there would be different physical processes you want to maybe simulate in order to make more accurate predictions. And you immediately come to the point that computing all of this would be quite computationally expensive. So you cut it into different pieces, as you see here, in order to use probably also different cores. And of course, think about that it's essentially not 2D, it's 3D, right? The atmosphere and so on. So this could be really an interesting endeavor. Just to show you a kind of appetizer that, of course, high performance computing being always intertwined with specific domains, right? We don't do HPC just for fun, to be Formula One in computing, to be the fastest. We want to use the fastest computing power to solve a real life problem. And here's basically the climate example, which is one of the key challenges for us in human mankind, maybe along medicine and others, but still something to really well understood with using computing. And you also can understand a little bit why we talked MPI now. You can imagine a cloud going over here, the US, a little bit, North America. Here we have this interaction with neighboring cells over time, right? We always would think about there's something moving, there's a process. Something over time is evolving. The weather is evolving over time. The physical processes based basically on all the different laws and equations is evolving over time. And basically with this, we have lots of interaction with all of the neighboring cells to exchange variables, to compute these physical equations, the physical formulas, and so on. And we will do this step by step in the course to understand a bit more what we mean by this. And of course, now you can think about when you have a problem like this, you always have different ways how to solve it. And here's a slide that shows you just the possibilities of how you actually can do parallelization in this. And here's a 1D parallelization method, which is obviously very trivial. And then you have a 2D parallelization where you have a matrix essentially. And then 3D, where basically you have here the overall domain, maybe the atmosphere we just seen based on some Earth science scenario. And then you have this kind of cut down into different processor decompositions, which might be not directly that any of these blocky representations would be on one core, on one processor. You see here, 8 of those are bundled into a processor decomposition, which is not the same thing. The domain decomposition is basically one thing, and then the other thing is how you really map this domain decomposition to the available cores. And more notably, maybe in some of the memory-bound applications, to map it to the available memory. Memory is important to get all the different variables right, to have a realistic simulation, perhaps. So you also want to think about that maybe even if not all cores are really working, you have memory there to really represent the domain better than you otherwise could on your laptop. Hence, this is also something when we talk about memory-bound applications and so on in later lectures. And here's a very interesting overview that even in 2D, you come to all sorts of different ways how you can perform a domain decomposition, and they all have their own rights in terms of message exchanges, overheads, in terms of reducing this overhead, or basically of computing capacity, of memory capacity, and so forth. I don't go into details, more schematic schematic way of view that you see really how could you do this domain decomposition. And here you see even with data parallel, which the domain suggests, you could even come to an idea of functional parallelism, where essentially every of the processors is doing, let's say, another different parts of the story. And a good example might be that a couple of those processes do the atmospheric model. Another one does the land surface model of your raining or your basically precipitation model. And then there's another hydrological model that interacts with the ocean model, and all of them work together intertwined. So they all have a different function. They simulate the atmosphere, the ocean, etc. But this would be called functional parallelism, governing perhaps by somewhat similar equations, but still in different domains or basically elements. And with this, we basically are in the more conceptual idea of parallelization methods. And the SPMD you already know. That's what we did when we thought about MPI in the last lecture. We said the single program, the same program really, all the time, but with multiple data. And we use the ranks to determine the application logic. And this is the SPMD. But we also think about the functional parallelism of MPMD, multiple program, multiple data, where we have maybe different coupled applications to make up the big story. And here we have the Formula One car, where maybe the simulation on the tire might be different from the others because it also has to interact with the road underneath to be accurate, while maybe the head and the higher part of the Formula One is much more concerned of having basically then the kind of flow in terms of speed, the stress levels on the material, and so on. And these are just examples of the many parallelization methods. And of course, they're both, let's say, ground or foundations really of how to do parallelism. But we will see in lecture 10 to 15, then in later parts of this lecture, how this is really reflected in different parallel application domains, why people are adopting different strategies, right? Because it depends heavily now on your application domain problem of how you do the parallelization, where it's beneficial. Now, a very simple idea also, when you think about data parallelism, would be, of course, a loop, right? And I think this is relatively low level in certain ways of thinking that, of course, when you have a simple operation here, that the array at the position E is only dependent on the position E again, essentially then you can really nicely parallelize this, let's say on 2 processors, and you just have the loop basically divided by 2 in order to solve that problem. And then of course you have the array E filled here with all the different iterations of these loops until 1000, but done in parallel. And this is of course something where, for instance, shared memory plays a big role because I can always influence this. So by this, of course, you can see, especially for shared memory programming, this kind of loop parallelization plays a big role. We will also learn in lecture 6, there are specific instructions, we call that compiler directives for shared memory for these loops, which we don't expose today. But of course, this is one idea of parallelization on a very small scale with shared memory within one node. And then, of course, if you go across node, you can actually combine this maybe by using MPI, what we learned already in lecture 2. So the domain decomposition is essentially a very important part. That's why we bring it early in the course. And you can imagine, while we think about it, it all seems to be blocky, right? And that's what I presented until now, but it must not be the case. You see also here, this blocky character, the 2D grid display, maybe one beach here somewhere in Iceland. It could be in the Westfjords, maybe Bolungarvík, simulating a little bit here, the big hill in Bolungarvík, and basically a little bit of the ocean around it, and so forth. So, but the key message to take away is that all is based on data. So we have to have this discrete definitions basically based on some data quantities. And it's not always that it's beautiful Cartesian, right? Like this here suggests. You could think about this globe where the Cartesian in a way is pulled over it, but of course they're not of equal size anymore because our world is not flat like here. So in a way, it's a little bit dependent, of course, of data that you have available. Maybe you have measurement stations which are not completely covered the whole terrain. You have to do averages, but still, of course, the key idea is then to have this grid and to somewhat map those to the different end processors that you have to compute the things that are happening here at the beach or at the mountain level here is basically, let's say, a little bit different physics. So we compute this differently with the data we have of the elevation here or the wave height here. And then with this come to a much more realistic simulation and have the computing power available to simulate this is of course a key concern in HPC. That's why we do it. So hence, there is not always this Cartesian grid, which is so beautiful, like here in this wave simulation. Maybe you have a so-called 3D grid which has this one value in the beginning. You have this kind of lattice, which has more emphasis on the corners to enable a sort of more smoother representation of the domain, but also, lots of data points. And then if you think about really cutting edge scenarios, you would say they're even more advanced domain decomposition. Think about race car. We're mostly interested in the, let's say, airflow around it. We're not so much interested in the more least parts of it. The same with the aircraft. We would say the turbulence created directly from the turbines is of our most importance, but what's happening more far away is of less importance. So you would basically compute what's happening around this race car or around the Airbus here much more in detail. And with this, you can carry on. We have examples in lecture 15, for instance, where you think about a very blocky character. Maybe Iceland is here somewhere. But then, of course, you can add scientific domain studies, rainfall, etc., more details. You can always add to have more realistic behavior of these simulations. So you would maybe basically cut down the domain into smaller and smaller pieces, because in each of these steps where you basically come from a very blocky to a much more realistic setup here, maybe to add more and more objects of study. So you need more computing, more variables, more memory, and basically to interact then and to make a wave propagation maybe throughout this part happening and to simulate all of that, or floodings and so on. You can use the MPI and the message passing between these different cells to really communicate, as we learn to send, receive, or even broadcast basically information. And you will also do this in this course in later assignments, which we basically will do to foster what we learn here with the kind of domain decomposition. Then another one is the formula race car design. Just to think about that basically how we do this, we would have a good parallelization method, think about the whole problem, but cutting into different pieces. Then you would have some good MPI code, thinking about how can the different parts be simulated, and then how we can differentiate between the different processes with ranks and so on, and maybe scale it among many cores. And then the real challenge is over time, then you want to simulate over time and having physical processes. So the interactions of this Formula One car with the air driving at certain speed will be key to the understanding. And this is a very advanced scenario already, part of CFD simulations we will have also in the course later. Maybe a very simple program or idea is this initial heat map here, where you think about the so-called heat dissipation, where you have initial heat map and you want to just basically over the time want to have the heat in the room, you as a supercomputer, but you directly need the point that basically the neighboring will be always very important to understand how am I in the next time period. And this is something where we come to so-called stencil methods, to the so-called Jacobi solver, which is more or less an iterative method to basically go more and more step-by-step closer to a simulation, which gives you approximations of the heat. And there also a different domain decomposition. You see simulating one, including 6 neighbor cells, 26 neighbor cells, much more details. And then you come after this 50 rounds, 200 rounds to a simulation. How would the heat be basically in the room until then? There are some interesting YouTube videos here around it if you want, that basically shows this Jacobi solver. But I think you get the message. Of course, we are always interested in time. Now, time is a problematic factor because we maybe not always have access to the next time period, and that's why we have to have this message changes. I think if you carefully look on this, and this is the idea of really have this heat dissipation computed by physical formulas by using an isotropic lattice, so really basically having, kind of the idea of going to a very proper domain composition. Still, when I want to compute the next time step, the delta here in time, what I need is from the neighboring cells, the data from the previous time step. So this is T0, the dark ones. T1 is the light ones. So in order to have the next time step, the light ones here, for this particular fellow, I need from all my surrounding neighbors, actually the heat it was in the previous time step. Then I know how hot I am. So it seems a bit interesting to think that, of course, to compute my own status, I need the input from all my neighbors. And this is one of the key considerations. And we will talk about this also in hybrid programming a little bit, but you see it here very well characterized. And here maybe a bit more with the T0 and T1. It's a very important technique, which is in many simulations actually implemented. So when you do this parallelization of this kind of two-dimensional Jacobi solvers, it's really an iterative method that every time step you have this message exchanges, and then basically of this end-to-end grid, we come to a solution over time by computing it. And with this, you basically have a very systematic way of doing message exchanges here in the basically domain specified by K and L. But the real problem is, of course, the idea that you may, over this domain, have not really access to the data you need in the next time step. We call that halo cells and ghost cells. So you introduce a so-called cell that is not really existing in your domain part, but is already part of the neighbor, and vice versa. This enables you to basically, before you compute now, and here we have the point that in order to have my next time step computed, where my heat is basically exact, I need the information from that particular fellow, but this is on another memory space. I cannot access it. So you make sure in the basically previous time step you send the message already was sent it, and MPI over to fill in this whole halo ghost cell the information so that in the next time step really this value can be computed. And that's how you bridge this memory gap areas, right? That's where MPI is now incredibly used to basically make use of this halo and ghost cell. And of course, we have more application scenarios later on. They also refer to different cost strategies. You can imagine, though, if you cut this domain decomposition, which is now an important word for you, you probably understand it more and more. You can imagine that this has direct impact on communication. One good example is this one, where you think it would not matter how I cut it. There would be always the same communication, but it's actually not true. If you cut it in these different pieces, which is essentially then 3 times having 16 communication adding up to 48, you can think that maybe a blocky representation here of doing domain composition will actually decrease the amount of communication necessary, because it's just 4 times 8, which is 32. And of course, think about that this communication is done per time step again and again and again to order to solve a problem. And with this, of course, we have just 4 domains, which have, let's say, less communication. So it really matters how you do domain decomposition. That's what I'm saying. And in lecture 10, we will review this explicitly by having also, let's say, different load balance issues, which you also will learn about in part of the next lectures, where there's many points on one and less points on the other processes. And in order to do a proper, let's say, domain decomposition, you rather don't want to put it here in the middle, as your brain would suggest in the beginning. You put it where the computing is, so in the middle of the heat here, so to speak, with many of the processes, if you want to do clustering. But this is something for lecture 10. We need much more basics to really go into this. The same is true if you want to review a little bit why functional parallelism is maybe a good scheme. For instance, leveraging the master worker scheme. Also, this will be something we have in one of the CFD simulations for you. So basically, it would be too much to bring it all in this lecture. Just an appetizer that we will have real life problems starting from lecture 10 really up to the final lectures. And then we'll also think about much more of this multi-physics simulations, the airflow around a race car, but also then, of course, of CFD codes in general, which is a very hot domain for HPC. So all of this has relationships to many different application domains. And I think that's why I basically stop here, let you enjoy a little bit the video. And you see Iceland is very prominent here with the Eyjafjallajökull volcano that actually was one of the HPC examples here, which are admittedly a bit data driven, but still add insights of different application scenarios provided by the Barcelona Supercomputing Center. Yeah, the Barcelona Supercomputing is a very interesting center. Not only they have very many specialists, of course, in all kinds of sciences, they also have the supercomputer in a church called Mare Nostrum. So if you want to see more on YouTube, I encourage you to look at Mare Nostrum. I was there, and it's really incredible to see a supercomputer in a church, which makes sense in a hot country because it cools down, of course, significantly already the environment, but it's also a very interesting demonstrator of a HPC system. Still, I think we finished for today, and we see you in the second part of this lecture.